Theorem 4, if f is differentiable at a, then f is continuous at a. Now, to prove that f is continuous at a, we have to show that the limit as x approaches a of f of x is equal to f of a. We do this by showing the difference f of x minus f of a approaches 0 as x approaches a. So the given information is that f is differentiable at a, so that is f prime of a is equal to the limit as x approaches a of f of x minus f of a x minus a exists. Now, to connect the given and the unknown, we divide and multiply f of x minus f of a by x minus a, which we can do when x does not equal a. So here we have f of x minus f of a, which is equal to f of x minus f of a over x minus a times x minus a. Now we're going to use the product law, and 2.6.5, we can write the following. We can take the limit on this side, the limit as x approaches a of f of x minus f of a, and that's going to equal the limit on this side as x approaches a of f of x minus f of a over x minus a times x minus a. Now we can apply the limit to both of these, so we have the limit as x approaches a of f of x minus f of a times x minus a times the limit of x minus a times x minus a. Now we know that from here, from up here, that f prime of a equals this. So we know that this entire piece here is f prime of a times, if we put in here the limit as x approaches a of x minus a, that becomes 0. So therefore 0 times f prime of a is equal to 0. So to use what we just have proved, we start with f of x and then add and subtract f of a. So we have the limit as x approaches a of f of x, which is equal to the limit of x approaches a of f of a plus f of x minus f of a. And then we're going to then apply the limit using the addition. So the limit as x approaches a of f of x plus the limit as f of x minus f of a, which we found here to be 0. So therefore, this becomes f of a plus 0, which is equal to f of a. Therefore, f is continuous at that value of a. Now, there is a note that we should pay attention to here. So, the note is that the converse of this theorem is false. That is, there are functions that are continuous but not differentiable. So, for instance, the function f of x is equal to the absolute value of x is continuous at 0, because we found that the limit as x approaches 0 of f of x is equal to the limit as x approaches 0 of the absolute value of x, which is equal to 0, which is equal to f of 0.